In today's video, I'd like to show you this. Now, before I go into too many details as to actually what it is, think of it as like a continuity meter on steroids. I like to call it the sound of resistance. It's a small project that I've been working on. It's not complete at the moment. It's still in the development stages, but I have a working representation of the basic idea. So in this video, I'm going to show you the basic concept, explain the various elements of how the device works, show you this prototype that I have on the bench here, discuss how to modify it to increase the range and usability of the device. So let's go. So a quick overview of the device before I show you actually what it does. Basically, I've got two circuit boards here that I've made. The first one has got a TL082 opamp and a few associated components. The second PCB basically consists of a CD4046 IC. We've got a little speaker here, a transistor, a couple of caps, resistors, etc. And again on this one we've basically got a transistor, some resistors, etc. It's powered at the moment from bench power, so it's currently on a plus or minus 9 volt supply. And I also have here in shop, this is basically a resistance decade board. I don't know if you can see in shop, but it has many ranges. Goes basically, this is the mega ohm range, 100 ohm, 10 ohm, 1 ohm and 0.1 of an ohm ranges. Now in this video I'm going to be concentrating on basically these two ranges here, which is going to be the 1 ohm and 0.1 ohm ranges. I'm not going to worry about any of this, so I'm going to keep all these jumpers in the top position, which is basically going to be effectively a short circuit. Let's actually power the device up. I'm actually going to pop that one off of there to start with. Okay, the device is powered up. So basically what I have here is I've got two sense wires here, which are these two grey ones. They're connected just through this multi-way cable onto the decade board, and then obviously there I can select resistances. So effectively this is just simulating measuring different resistances, and as you may have guessed, in this particular video I'm going to be concentrating on low ohms. So I'm just going to take this jumper and I'm going to put it onto the 0 link, and we can hear that we have a tone. So now if I then take this jumper and I move it, for example, to the, so this is the 0.1 ohm scale, 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, 0. Okay, so then we'll go to 0.5 and then we'll go to the 1 ohm. So this is now 1.5 ohms. We can hear the frequency is much lower. We go to 1.9 ohms. So I'm back here again actually 3 days later, because during the edit I realised that you couldn't really hear the beeper. So I've changed the sensitivity of the microphone a little bit and we'll have another go. So we'll start at, this is 2.5 ohms. And 1.5 and 0.5. And if we go from 0.9 to 0.1, 0.5, 0.9, 0.5, 0.1, 0.7. So if we go, we'll just do a direct one, so we go from 2 ohms to 0 ohms, and then if we go to 0.5 of an ohm, which is that one, okay, and we can hear the tones. So basically what this guy does is it measures the resistance on the two sense wires, and it will give you a tone, and the frequency of that tone will depend on the resistance that you're measuring. So the way I have this set up now is basically to measure around 2 ohms to 0 ohms, but the device is configurable. It can measure potentially up to around a megohm with a similar kind of range. So I have set this circuit up to measure low ohms, as I say, from around 2 ohms down to 0, and it will give a frequency range of around 2 kilohertz ish for the highest resistance, going up in frequency to the lowest resistance. Now I only have this little, it's basically a motherboard speaker here. Its frequency range is quite limited. I'm kind of an old guy, so my hearing range is kind of limited as well, so I've got the frequency, upper end of the frequency set for around 8 to 10 kilohertz thereabouts, and the low end around 1 to 2 kilohertz. As I said at the start of the video, it's kind of like a continuity mode on a multimeter, but on steroids. So it does give you not just a single tone. So the continuity mode on a multimeter will basically give you a single tone if the resistance is below a certain threshold, usually around 150 to 100 ohms, somewhere around there. This device takes that one step further by giving you a variable frequency tone depending on the resistance that you're actually measuring. The reason for the concept of this device is basically if you've just got a continuity mode on a standard multimeter that just beeps below a certain resistance, it doesn't necessarily tell you what that resistance is. It's just giving you an indication that it's below a certain threshold, and that threshold can vary quite a lot between manufacturers. The concept of this is that you can probe around on a piece of equipment. You can actually hear the rough resistance that you're measuring without it looking at the meter every time. So if you're going through a motherboard and you're looking for low resistances, and you may have a bit of variation, you might have a short circuit on a component somewhere, and you're not measuring near that short circuit, so your resistance is going to be a little bit higher from one track to another. By listening to it, you can distinguish the difference between those two resistance readings audibly without actually having to look at your meter every time. I think it's a great way to speed up fault finding under certain conditions. So that was the idea behind the device, that was the concept. Let's go ahead and I'll show you the various elements in this unit and outline the modifications that you can make to it to change the ranges at which it works over. So the basic concept of measurement is actually quite straightforward. What we're actually doing is we're using an op-amp here, as we can see in this illustration, and we're supplying that op-amp with a reference voltage through a resistor, and then we're actually measuring the test probes of the points here. So the resistance that we're measuring is actually providing the feedback for this op-amp. Just very generally speaking, in this condition, if the resistance that you're measuring is equal to the resistance of R1, then your voltage out will be pretty much the voltage in, the gain of 1. If your resistance measuring is approximately half of the resistance value that you have for R1 here, then your output voltage is going to be pretty much half of your reference voltage, so it's a gain of 0.5. And the same token, if your resistance measurement is say 1,000th of your resistance here, then your gain is going to be 1,000th, and therefore your output voltage will be 1,000th of your reference voltage. So in this example, if for example your reference voltage is 2.5 volts and your measurement resistance here is 1,000th of this value, then your gain will be 1,000th. Your output voltage will be 0.0025 volts. So that necessarily isn't overly useful. It's okay if you want to measure higher resistances, but if you want to measure lower resistances, if you want to measure down to 0.1 of an ohm, for example, then your output voltage here isn't really going to be very usable for anything. So then what we do is we basically take the same circuit concept in the first part, which is then in this circuit diagram I've actually added a second op amp. So now the first one that we saw is U1A. It's exactly the same principle. We take the output of that op amp and we feed it into another op amp, and then we can then increase the gain to give us an output which is more usable for measuring much lower resistances. So again, in this example, we saw the gain of this section could be as low as 1,000. So then we really want the gain over here to be maybe in the range of 100 to 1,000 to then give us the same output voltage as our reference voltage, but measuring in a much lower range. To do that, obviously the gain of an op amp basically is the this resistor divided by this resistor. So the value of those two will give you the output gain of the op amp. So in this example, say if we had this resistor was 1k and this was 100k, this would give us a gain of 100. The idea of this is basically so you can offset the output. So normally, as in the first stage, you would connect the this pin to ground, but in the second op amp, what we've done is we've connected it through basically a potential divider, and therefore we can offset the output voltage to a level within the range of the potentiometer. So what I've described just there with the op amp is basically this circuit board. Now this does have some additional components on because I've been experimenting with this to get it to do what I actually want it to do. Actually, to be honest with you, this was the first version done on a piece of breadboard, which basically is pretty much the same as what I've got laid out on these two pieces of Vero board. So the op amp section is the first section here. Again, I have added lots of extra components. This can be a lot simpler, but basically what we have here is a TL082, which is a dual op amp. We've got a plus or minus 9 volt supply, I think, at the moment. Yep, from a bench power supply, linear power supply that is, not a switch mode power supply. We've got the various gain resistors set around here and a couple of potentiometers. I have got an LED on here just to show that the power is actually on this, because it doesn't actually give any output when there's no resistance on the input, and that was a little bit confusing, so I just wanted to give myself a visual indication that I actually had power on the thing. That doesn't need to be in the final version. I have here, this is a TL431 voltage reference. This is actually a 2.5. I have also got here a TLV431, which is basically the low voltage version of the TL431. I think this is 1.25 volts. and this is 2.5. I did actually stick with the 2.5 because it gives me the kind of range that I'm after, with the gains that I've selected on this particular design. I have got the potentiometer, which was shown in the description. This board does have the addition of a transistor over here and some extra components. That's basically to invert the signal and to condition the signal to an appropriate level to feed over to this guy. I will show you what I've done there in a little while on the circuit diagram. So basically this board is measuring the resistance on the two probe wires here, converting that to a signal which is suitable to transfer over to this board. So then we're going to talk about this guy. We'll do that now. So the second board is based around a CD4046 CMOS phase lock loop IC. The data sheet is a little bit unusual for this IC because it doesn't actually give you any application examples. Now there is actually an application note PDF that goes with this as a separate data sheet by Texas Instruments, and the section that we're going to be interested in is the voltage controlled oscillator, which starts at page 15 here. So I won't go into too many details on this. Basically what I'm using this for is to create a frequency, a square wave output, variable frequency dependent on the input voltage, which is basically what a voltage controlled oscillator is. Basically create a square wave with an output frequency of around 1 to 2 kilohertz at the bottom end to around 8 to 10 at the top end. To achieve that, basically you need to do is to add one capacitor to the C1 position here and one resistor to the R1 position here, and depending on the values of those two we can get a square wave within the frequency that we're looking for. So I have in fact simplified that, and although you can't see what the resistor is because I've chopped it off, that's a 100k resistor and it's a 4.7 nanofarad capacitor. So here is the actual schematic for the output. So you can see, taking the output, the frequency out, goes through some signal conditioning, and then basically it drives the base of an NPN transistor. This is again to provide a bit of extra drive to enable us to drive a speaker. I've actually got a potentiometer in here to control the volume. This is just for the volume, and some signal conditioning. And as I mentioned earlier, there is another transistor on the first board, and basically that is acting as an inverter and a signal conditioner to take the output from the second stage of the opamp and drive the 4046 voltage controlled oscillator input. This is the circuit that I have so far. As I said, it's not finalized, it's still work in progress. And as I said, I originally had a TL-V431 in here. I have actually replaced this with just a TL-431 for now. It seems to be working quite well. As I said earlier, so the gain of the first stage is basically determined by the resistance that you're measuring, as opposed to a 1k resistor that I have for the input resistance. Then the second stage of the amplifier, I've actually got 100k over 1k, so it's going to give me a gain of 100. The offset here is a 47k pot and a couple of other resistors here. We're then driving the first transistor through another 100k pot, so the output is inverted here and then drives the 4046 with the variable voltage to create a frequency depending on that voltage, and then that goes on to drive the speaker. Now, as I said, I have this configured with these values for measuring low ohms. I've got 1k here to give a gain for this amplifier, and we've got 10k here to give the gain for this amplifier. As I said, this is a configurable circuit, so in fact we could switch different resistances in this position and also in this position to vary the gains of the amplifiers to change the measurement range all the way up to, I think, probably around 1 megohm. But I specifically want this to measure low ohm, so I'm happy with this circuit as it is. For that purpose, it's a very simple process to modify this circuit to measure different ranges, similar to how you'd select different ranges on a multimeter. You could select different measurement ranges on this, and then the frequency sweep will be within the range that you select. So there you have it. The project's called The Sound of Resistance. It's a simple device that enables you to audibly measure resistance, which I think is quite a novel approach. So I hope you like this one. Please, if you enjoyed this video, subscribe to the channel, and I look forward to hearing any comments you have on this. More than happy to discuss any of the design elements and how to modify the design. So thanks for watching.